Okay, so this is our last and final example for our review for the concepts and principle of shearing stress on beams for structural steel. Okay, so a wide flange and a channel having the following properties. So you have here the properties for your wide flange section and then your channel section. Then you have here also your section. This is how they are connected. They are connected with a rows of bolts connected at the web of the channel and to the flange of the steel section or the wide flange section by means of a 60 mm diameter bolt having a shear capacity of 100 megapascal. Okay, so you have here the allowable bending stress for channel is 118 megapascal, and then the allowable bending stress for the wide flange section is 138 megapascal. Okay, so our objective for this particular example is to determine the moment capacity of the composite section. Next is to determine the safe uniform load which the section can carry, and then we call this one built up section rather, not composite. Okay, for the built up section. Then you have here number 3, determine the spacing of the bolt. And then number 4 is determine the theoretical cutoff point of the channel. Okay, I think we do not have a span for this one. We'll just assume a span later on. Okay. Okay, so first is your moment capacity. When you say moment capacity, it is the maximum moment which the section could carry. Okay, so basically for us to calculate for the maximum moment that the section could carry, that would be based from your bending stress. Okay, now for your bending stress is again FB. Sorry for the wiggly. Okay. F bending is taken as MC over I. Okay? So in this particular case, you have your FB can be equated to the allowable bending stress of channel or the allowable bending stress of the wide flange. Which one of these is to be used, we'll find that out later on. C is the distance of the neutral axis to extreme fibers. It's either tension or compression. We'll find out which value are we going to utilize later. Now, I here is the moment of inertia of the section. You're given here the moment of inertia for the individual sections. Moment of inertia x and y for the wide flange, moment of inertia x and y for the channel. Okay? Now, for you to calculate for the moment of inertia of the section, basically, you need to make use of transfer formula for you to calculate for the moment of inertia of the composite or the moment of inertia of the built-up section. Okay? So, moment of inertia, making use of transfer formula, moment of inertia about the neutral axis is taken as the summation of the individual moment of inertia plus the cross-sectional area times d square. D here is the distance between the centroid of the individual geometry with respect to the neutral axis. Okay, I is the individual moment of inertia. Now, since we are dealing with bending stress, which is about the strong direction of your wide flange, basically, we will be making use of the strong direction for the wide flange, IX. What about for the channel section? What are we going to use for the channel section? Now, for the channel section by default is oriented on this particular manner. Okay? In this particular manner, your strong direction is this one. So, IX is on that particular direction. And then your weak direction is on this section, IY. So, basically, if this one is reoriented such that it can be a built-up section, attached to your wide flange, basically what we will be utilizing in your channel is your IY. Okay? So IX for wide flange and then IY for the channel. Okay? So that gives us the values for I for both sections. Next, A here is not a problem. Basically, you're given here A of wide flange, A for channel. So next is D. Again, B is defined as the distance between the centroid of the individual geometry or cross-section of your components with respect to your neutral axis. Now, if that's the case, you need first to locate your neutral axis. Okay? Now, for this particular solution, we will just make use of Varignon's theorem. Now, Varignon's theorem states that the moment of the resultant is equal to the moment of the components. Okay, so in this case, let's just make use of the base of your wide flange as your datum point. Okay, so this one will be your datum. Now we are locating the neutral axis. Let's assume that it is somewhere here. Now the distance between the datum and the neutral axis, let's denote that one as board Y. Okay? Now you have here your centroid of the wide flange section. Of course, common sense will tell you that that is at the mid height. Let's denote this one as Y1, which is, we can have that one as what? Basically, that's the mid height of your wide flange. That is 470 divided by 2. 470 over 2. Okay? While the other one, you have here the centroid of your channel is somewhere here. Okay? If you try to go back here, your centroid is somewhere here. Now you have here a given value of x. Basically, that x is with respect to the face of the flange. Okay, so that one is x, which is in this case 20. Okay, so if this one is reoriented horizontally, so basically with respect to the top of the composite or the built-up section, going downward, you have the location of the centroid of your channel, which is 20. So basically, from this point to this point, to the datum, we can calculate for that one. Basically, it would be the height of the wide flange section plus the thickness of the web of the channel minus 20. Then that would give you the height or the location of your centroid with respect to the datum. Okay, let's repeat. That is 470 plus thickness of flange or thickness of web rather is 10, and then less 20. That would give you 460. Okay, now since you have calculated that, we can now have your Varignon's theorem. Okay, or yes, Varignon's theorem. So Varignon's theorem, you would have here moment of the resultant, that would be total area times board Y is equal to the summation of individual areas times their lever arm with respect to the datum. Okay, both lever arms for component and the resultant are based from the datum. Okay, so area of total area, that would be simply equal to what? That would be simply equal to 18,400. That's the area for wide flange plus 64,300 area or 6,430 area for your channel times board Y is equal to, beginning with the wide flange, you would have here 18,400 times Y. Y for wide flange is what? 470 over 2. Okay, and then plus you have 6,430 times Y for the channel section is 460. So with that, you can calculate for board Y, or basically that is the location of your neutral axis. That is 293.0 2662. That is in mm. Now, making use of your transfer formula, you would have here I and A now, or moment of inertia with respect to the neutral axis, is equal to, starting with your wide flange, that is 726 times 10 raised to the 6, that is the moment of inertia of about x of your wide flange, plus area. Okay, area for that one is 18,400 times d. Again, d is the distance from the centroid of your section to the neutral axis. So basically this one is your d1. Okay, so d1 is calculated as barred y minus y1. Okay, then take the square. Okay, so going back, you would have here 293.6 or 2662 less 470 over 2 square plus. Okay, so this one ends your wide flange section. Next, we go to channel. Channel, you would have here IY in this particular case, that is 3.4 times 10 raised to the 6, and then plus you have A is 66,430 times d square. D in this particular case is, again, going back to the definition, distance of the centroid of the section, as that one, to the neutral axis. Neutral axis is this one. Let's write this down, neutral axis. So basically, you would have here your D2 to be this one. Okay? So that would be what? D2 would be equal to Y2. I forgot to denote this one by Y2. Y2 less Y, or that would be 460 less barred Y. Okay, so that would give you 460 less 293.2662 square. Okay, so your moment of inertia of the built up section is equivalent to 970.622 1 times 10 raised to the 6 mm the fourth. Okay, so that is your moment of inertia. Now you can proceed for your moment capacity. Now for your moment capacity, let's go back to the problem of which bending moment or bending stress are we going to utilize. Okay, now if we were to analyze the situation, we can calculate for the maximum moment if you have maximum bending stress. Okay, now in this case, your maximum bending stress is you can have a maximum value if you have your maximum bending stress rather. Okay, so your maximum bending stress, or comparing these two bending stresses, you would have this one to be higher than this one. Okay, so that is one criteria. Another is your C. Okay, now basically you would have a higher amount of stress if your C is at a higher value. So basically, in this case, if you try to go back to your section, C can be measured with respect to the neutral axis. It can be this one or it can be this one. Okay? Now, in this case, C, if you're making use of the channel, or if you were to consider the compression flange or the compression section or compression part, then you will make use of the bending stress for the channel. Now if you will make use of the tension side, then you will be utilizing the bending stress for the wide flange. Basic principle states that if this one is being exposed to compression, then it's rightful to say that this one is to be utilized. Same is true with this one. Okay, so going back. Okay, so if we were to calculate for both, okay, so let's have here F bending utilizing your channel, or yes, channel, 118 newtons per mm square is equal to, okay, this is our formula, 118 newtons per mm square is equal to your moment which you're looking for. C is what? C is the overall depth minus barred Y. Overall depth would be 470 plus 20 less 293.2662. Okay? Divided by I. You have there 970.6221 times 10 raised to the 6. Then you have your moment capacity, M. Okay? So, for your moment capacity, that would be equal to that would be equal to 582.1745. Okay? Next, if you were to utilize the tension side of your section, you would have here 138 newtons per mm square is equal to M times 293.2662 divided by 970.6221 times 10 raised to the 6. So you would have here a moment which is equivalent to 456.73. That is in Newton, kilonewton meter. Same is true with that one. That is in kilonewton meter. Okay. So which one are we going to use as your moment capacity? Now, if we were to apply, if we were to apply this particular moment to your section, then it would fail on the tension side. Okay, basically this is the capacity of the compression side. But if we were to apply this moment to this section, since this one is lesser than the capacity of the compression side, basically your compression side can carry this particular moment, but this one is the capacity of your tension side, so therefore this moment cannot be, or your tension side cannot carry this particular amount of moment. So it is rightful to say that your maximum capacity is 456.73 kilonewtons. Okay, so next is your safe uniform load. Okay, let me just check what is the span for this particular example. What is the span for this example? Do you have a span for this example? Yeah, it's 9 meters. Your span is 9 meters. Let me insert that one. The span for this one you have here is simple span of 9 meters. Anyway, it's just an example. Okay? So, a simple span of 9 meters, you would have here determine the moment capacity of, determine the safe uniform load. Okay? So, since you have now your moment, and then it is only simply supported, then moment M is equivalent to WL square over 8. Okay? So, from the derived equations or derived formulas from strength of materials or theory of structures. So, you have here 456.73 is equal to W times 9 square divided by 8. Okay, so you would have a uniform load, maximum uniform load of 45.11. That is in kilonewton per meter. Okay. Next is spacing of bolts. Now, spacing of bolts, going back to principles again of your strength of materials, spacing of bolts is taken using the formula S is equal to Ri over VQ. Okay? So, let's go to their definition. What is S? S is the spacing. R is the shear force which is carried by your bolts. I is the moment of inertia. V is the amount of shear carried by your section. Okay, and then Q is the moment of area of the section. Which section? Basically, the one that is connected to the main section. That would be the channel. Moment of area of the channel with respect to the neutral axis. So we would be calculating for the following. Okay, so we already have calculated for I. Okay, for V, we do not have the shear force, or the, yes, we have the shear force carried by the beam. Okay, we do not know that yet. Next, you have here the shear force of the bolt. We do not know that yet. And then we do not know Q. Okay, so what we have only is this variable. Okay, so we are to derive this two. Okay, now let's first have R. What is R? R is the shear force carried by your bolt. Okay, R using simple stress. Okay, R is equal to your allowable shear stress FB of bolt times the diameter of, or sorry, area of your bolt. Okay, so you would have here R now is equal to how much? That is 100 newtons per mm square times pi over 4 times diameter square. So there are two shear planes for your bolt. This one and that one, that would be 2. So multiply this by 2. Okay, so your shear force R is equivalent to 40.2123 times 10 raised to the 3 newtons. Okay, next is your Q. Okay, let's have now Q. Q is the moment of area of your channel only. Channel only. Because why channel? Because it is the one which is above your it is the section which is connected to your wide flange section. So calculating for Q, you have the area of the channel, that is 6430, multiplied by the distance of the interface, or distance of the centroid with respect to your neutral axis.